Yeah, so as Roland told you, I want to talk about extreme events, which I'll use the shorthand X events for, and resilience and complexity. Can you not hear me? Okay, how's that? Okay. And when I planned this talk, I thought that I would give my elevator speech telling you how I think these three concepts are interrelated in various ways. But when I walked in this building and saw this Pater Noster outside, I think that I might have to use an extra 5 minutes in order to squeeze it all in. So let me start with X events. Incidentally, this is a topic close to my heart because I'm head of a small exploratory study at IIASA on the question of extreme events in human society. And in particular, that means the kinds of extreme events that are caused by human beings, human action. So we are not looking at floods, windstorms, earthquakes, hurricanes, etc., other than if they, like in Japan, if the natural extreme event gives rise to impact in the human society, and that the real extreme event is that impact in human society which was caused by human inattention and inaction. It wasn't caused by the earthquake, it was caused by human error, what we're seeing in Japan, even to this day. So, okay, let me start with X events. And here we go. What do we mean by an X event? What is an X event? Well, the conventional view is what I've listed up here at the top. That's usually the picture that people have in their mind when they think about an extreme event. I think it's too narrow, as indicated by the second half of this slide. I think that X events come in many sizes, shapes, colors, and forms. There's no such thing as this is an X event or this is not an X event. It's a grayscale kind of phenomena. And that these notions I put in here, the unfolding time, how long does it take for the event to actually, from its beginning to its termination, the impact time, how long is the impact of the event actually felt, and something I didn't put on here, the overall, call it impact magnitude. What is the total impact of that event? All of these three things are interwoven to create what the degree of, let's say, Xness of an X event. And they don't necessarily have to be bad. They can be good. There are good X events also. And you wonder, well, why do we always think of them as somehow catastrophic, negative, awful, to be avoided, and so on? Well, for those of you who took a course in thermodynamics, the basic answer to that question is the second law of thermodynamics, which essentially says it's a lot easier to tear something down than it is to build it up. So the positive or good X events, if you like, almost without fail, are ones that have a rather long unfolding time. Like, I'll give you an example. The development of agriculture and the domestication of animals. Now, that was an event that started maybe 8,000 years or so ago, and the impact is still being felt today. So it's still unfolding. The unfolding is not finished even for that event, but it certainly was a dramatic, extreme event, at least from the perspective of human life as we live it today. So let me first of all go to the so-called, the one common feature on both these lists, the rarity of the event, or you might think of it as the surprise level. It certainly is not sufficient to be an X event that it just be rare. Rarity by itself is not enough to be an extreme event. There's something else involved, and I'll come to that in a minute. But just to emphasize this rarity part, here's a picture, a two-part picture. Up at the top, you see a normal bell-shaped curve and a so-called fat tail distribution, one in which the extremes are a lot fatter, if you like, than with the normal regime, the normal curve. The normal curve is the blue one, by the way. The gray one. And when you look at this picture, And you read stories, people saying, oh, fat-tailed distributions, that's what caused the financial crash, too much risk, and so on and so forth. You look at this first picture, and you see that hatched region, and you say, well, this doesn't look so much. It doesn't look like it's so dramatically different, and so on. But what really matters is not the first picture, it's the second one. In the second picture, you see the blue curve is for the normal bell-shaped distribution. The red one is for a fat-tailed distribution, so-called Cauchy distribution. And what this graph measures is the likelihood of seeing an event in the bottom. The scale along the bottom is standard deviations away from the mean. And the likelihood of seeing a 1, 2, 3, 4 standard deviation event away from the mean. For the bell-shaped curve, it drops off dramatically. By the time you get out to 5 sigma, it's essentially 0. And notice, though, the vertical scale, each one of those horizontal lines is 10 times greater than the one next to it. So what you end up with from this picture is that if it is a fat-tailed distribution like the Cauchy, that the chances of getting a major event far away from the norm, 3 sigma, 4 sigma, 5, it's almost exactly the same. There's almost no difference. And any of those cases is thousands of times more likely than the same kind of an event if the space of events is a normal distribution. So this second picture is why the fat-tailed distributions matter. The extreme events, the surprise events, the rare events, they're a lot less rare if you have the fat-tailed distribution. Now, a second picture that relates to the rarity issue, but is a little bit more directly an extreme events picture. I like this picture a lot because it shows you, first of all, that the extreme events, without exception, they occur as a change of trend. Whatever the current trend is, and if an extreme event happens, that trend changes. And this picture shows you where the changes happen. They happen at these points A, B, that I've marked A, B, and C. And it's a mathematical theorem about this picture that in the set of all time points along the horizontal axis, those points where you have a turning, critical point, they form what probabilists call a set of measures 0 in the set of all time points. Now, informally speaking, what that means, if you pick a time point at random, you have probability 0 that it's going to be a turning point. Probability doesn't mean it's impossible. That's probability 0. Now, when you look at this picture and see, well, what's going on away from the turning points, away from the critical points? Well, nothing's going on. The current trend is just continuing. Whatever the current trend is, whatever is happening today, tomorrow's going to be just like today, except a little different. It's trend following. And this picture is exactly why so many so-called futurists make a huge living every year telling their customers tomorrow's going to be just like today, except a little bit better, or sometimes a little bit worse, trend following. And I tell you right now, you should not be willing to pay a single penny for this kind of so-called futurology, because you can do it yourself. You can do it yourself. As long as you know that you're not near a critical point. That's where there's real gold, not fool's gold, is identifying where are those points A, B, and C. When are you near or in the neighborhood of a turning point? Because that's the only place where the extreme events are going to happen. But even they are not enough for an extreme event. For an extreme event, that turning point can't be just any old turning point. In general, it has to be a sharp turning point. It has to be one where the curvature is very high at that point. The greater the curvature, the more dramatic the turning point, the change of trend. So I leave that information with you as far as extreme events are concerned. X events it's a necessary condition that it be a turning point, but again, it's not sufficient. And those turning points are rare, very rare, in the space of all time points. Maybe we should be grateful for that theorem. Okay, now let me turn over to the problem of complexity. Sometimes it's useful in life to go back and look in the literature and see what people were thinking decades ago. And here's something that somebody was thinking decades ago. In the 1950s, it was called in those days the Law of Requisite Variety. I've slightly renamed it here. The law, in modern terminology, the Law of Requisite Complexity. And the statement is the following. This was by Ross Ashby, a cyberneticist. There wasn't even a field called system theory in those days. And Ashby's theorem, if you like, can just be stated very simply. Only complexity can destroy complexity. So what he had in mind is, if you have a system that's supposed to be regulating or controlling another system, the complexity of that regulator has to be at least as great as the complexity of the system that's being controlled. Otherwise, you won't get full regulation. Well, I don't think it has all that much necessity for regulation. It's in the context of X events, complexity mismatches are the early warning sign, if you like, that you're getting into a danger zone. And almost without exception, every major X event comes about when the complexity of one system gets too far out of balance with the complexity of the system that it's in interaction with. And if humans don't step in to narrow that gap, bring them back into balance, then nature will step in to do it. And not by nature, it might be human nature, not just nature. And the way nature does it is not nice and it's not gentle, it's extreme. You get a crash. And here are a couple of recent examples. The so-called Arab Spring, where the two systems in interaction, governments and the public. Japanese earthquake, I said something about this a moment ago, the financial crash of 2007. And those of you who live here in Vienna, if you dig back into, well, actually you don't have to be in Vienna, into the newspaper files, I wrote a rather longish op-ed article about all of this stuff in the Vienna newspaper Der Standard in the issue of April 16. And so you can get, I'm going to pass on out of here because the time is disappearing faster than money. Yeah. So, or you can write a note to me at that email address that was on the opening slide, and I'll send you a copy of that article, and then you can get more details. Okay, now, what about if we're going to use this in a social context? I'm working up to resilience, I promise you. What is social complexity? Well, there's by no means any agreed upon definition. In fact, there's at least 50 definitions in the literature floating around about what you mean about complexity itself of a system, a physical system. But one thing I can say is that it's tied up very closely with the idea of degrees of freedom. How much flexibility does the system have to take actions when it's in contact with another system? And I want to emphasize this point because I don't think complexity itself is an intrinsic property of any system. There is no such thing as an isolated system that has, in and of itself, a level of complexity. The complexity is like a lot of other convenient everyday words, truth, beauty, justice, etc. It's in the eye of the beholder as much as it is in the eye of the beholden. And so it's a relative concept, a relative notion. So if you ask me, I'll say the same thing about resilience. If you ask me, how resilient is this system? My first question to you is to say, with respect to what? How resilient is it with respect to what? Because I think it's meaningless to talk about a system being resilient without talking about its environment. So that's my next. Oops, it's not my next picture, sorry. No, it's the one after this. So that's the first point on this slide. Resilience is a property of a system together with its environment, together with some other system or systems that it's in interaction with. And so it's a relative concept, and my conjecture, which I'm actually working on right now by gathering examples, is that the greater the resilience, the smaller the complexity gap. The most resilient systems with respect to another system are the cases when the two systems are basically in harmonic balance with each other in notion of complexity. And finally, here's a short list of research questions. How to measure social complexity? Well, first of all, let me point out that it's not necessary to create a number, because we're not talking about the complexity of a system in isolation. What I'm interested in is how do you measure the gap between two systems? And secondly, you don't even have to attach a number to that gap. To be useful, all you have to do is basically act like if there's a thermometer on the wall in this room, that thermometer has a brain which has three states, and those states are, it's too hot in here, it's too cold in here, or it's just about right. You don't need to have the temperature. And I think it's the same story here. Talk about complexity gaps, you can say that gap is small, it's getting too big, and you're in the danger zone. And of course, it's not a fixed number. These complexity, they're always changing. It's a dynamic process. So the one place where you almost never be is at the place where the two systems are exactly in balance. And if they are, they're quickly moving apart again. But it's a question of how big the gap is that can be sustained before you have a crash. And I'm just now finishing a book on this whole stuff, and I've got lots more stories to tell you, but this is my paternoster version of the story, so I'll let it go at this and turn the floor back to Roland. Thank you.